Hello. We're about to start, and before we do start, I just wanted to take a moment to have a moment of silence for the victims of the earthquakes. So if everybody could please be quiet just for a little bit. Thank you. Okay, thank you. We can begin. I'm going to put in a quick plug. Geophysics Nacional, which is in Mexico, is an English journal. We have a special edition for these two earthquakes. It's coming up. The deadline is May 30th. Quick plug. Okay, now we're going to begin with our first speaker, Vala. Please come to the stage. Vala Hjorleifsdottir. She's going to talk about the inversion for the 8.2, the first earthquake, the Tehuantepec one.
Good morning, everyone. So AGU insists on putting names of all the authors, but normally we present these things under the name of UNAM Seismology Group. So this is a group effort by a lot of people at both Instituto de Geofísica and Instituto de Ingeniería, Geophysics and Engineering Institutes at UNAM, plus some collaborators abroad. So I'll be talking about the magnitude 8.2 Tehuantepec earthquake in Mexico that occurred on September 8th. So this one occurred in, do we have a pointer? Use the mouse maybe? So let's see. And so that one occurred where, this is Mexico or central Mexico.
Make sure it's on the screen, right there. Click it.
Huh?
Click the button so it relines. So it's,
no pointer. Okay, so but you see the arrow. So where the arrow is, that's the Tehuantepec gap. And this figure shows earthquakes, rupture areas of large earthquakes in Mexico in approximately last 100 years. And so what we see is that mostly the large earthquakes center on the coast. They occur on the subduction interface. And each segment of the subduction zone will typically have earthquakes every 30 to 50 years. And these earthquakes are typically magnitude, the largest ones are magnitude 8, and many of them are 7.5, 7.3s. And the convergence rate in the Tehuantepec area is about 7 centimeters per year. And this is one of the gaps. You see there are two gaps, one in Guerrero, which I would like to point to, but you'll just have to figure it out for yourselves. And so there are two gaps, one in Guerrero and one in Tehuantepec, where the red arrow is. And so if we have, so the convergence rate is 7 centimeters per year. And this area, as you see on the topography on the seafloor, is intersected by the Tehuantepec Bridge. And so next I'm going to show you this, another enigmatic plot for the Mexican subduction zone. It has the same x-axis, so it's longitude or distance along trench, but the y-axis is time. And so what you can see there as dots and as horizontal bars are earthquakes. And so most of the region has had earthquakes in the last 200 years. But the gray shaded areas are where we have gaps. And so since this article was published in the 80s, how very kind of you, thank you. So since this paper was published, we have had several earthquakes, and these gaps have been slowly filling. And so there was an earthquake in Jalisco in 1995. There was the 1985 Michoacan earthquake. And we have had two earthquakes in what they call the Ometepec Gap. The two gaps that are unfilled is the Guerrero Gap and the Tehuantepec Gap. So obviously we have been worried about this region for a very long time. And it seems like the Tehuantepec area has not had a large earthquake in the last 200 years. And so if we think about it that way, and with the convergence rate, we see that there should be a slip deficit of maybe 14 meters on the subduction interface, supposing it's not creeping, which it may very well be. And so that's sort of the back history. And now I move on to what we did to study these earthquakes. So first I'm going to show you two slip inversions for the slip on the fault plane. And the data that we use is, in the first method, we use the extended fast finite fault package. It's a simulated annealing inversion method that uses wavelets. The data are P and S waves, Low and Rayleigh waves at teleseismic distances. And here is a sample of the data set. And so surprisingly to almost all of us, I think in Mexico at least, this earthquake was not the expected Tehuantepec earthquake on the subduction interface, but rather it was a normal faulting event on a very steep fault within the subducting slab. And so here is, to move quickly, here is the result from this inversion. And so what you see here is effectively a surface projection of this near vertical fault. And so it looks very narrow, but it's because you're looking at it from above. And so what we can see is that the rupture started out here somewhere, and it propagated towards the north with the large slip patch somewhat removed from the hypocenter. And so here we can see the side projection. So this is now depth, so projected onto a vertical plane. And so what we see is that the rupture started at 57 kilometers depth, and not much slip near the hypocenter, and then it had a very large but compact slip patch of about 40 by 60 kilometers. And the maximum slip that I obtained in this inversion is about almost 15 meters. So it's very compact and very large slip. And so another thing that we can observe here, so these are relocated aftershocks in the first 2 days after the earthquake, and then we'll see more in a little bit. And what we see is that they are sort of to the end of the fault, and here they are projected onto the fault. Unfortunately, we do not have many stations in this area, so they are not so well located, but it looks like they're sort of surrounding this big fault patch. Also, what we can see is that this rupture is not really parallel to the trench, but more it's parallel to this fabric on the seafloor. And so it seems this may be a reactivation of some of these faults in the incoming oceanic plate. We also did an inversion using regional and local data. And so here is another, I'll show you quickly another inversion. And what we see is that we obtain, within the resolution of these kinds of inversions, we get a somewhat similar solution. So it starts again at 57 kilometers. It ruptures principally to the northwest. And here we have a large slip patch, again, with slips of up to 15 meters. And so now I'm going to move on to the aftershocks. So the aftershock sequence was very productive. The people in the area were very much affected by this high activity. They were woken up all the time by constant aftershocks. But they were really evolving through time. And so what you see here are the locations of aftershocks and colored as a function of days from the main event. And so what we can see is the earthquakes that we saw in the previous plots that are basically these blue events. But then we see that there is sort of like this fault here, there is some other structure here, and then there are these localized structures further inland. And so I'll show you in the next slide these cross sections through this segment A, B, C, D. And so here's the cross section. Here is the slab contours. And here we have a contour that indicates an estimated lithospheric thickness of 35 kilometers. And so we see that in this top segment here, it seems like most of the seismicity is in the overriding plate, but there is also some activity on vertical fault within the slab. And so here is the Tehuantepec ridge. So it's clear that at least the the aftershock sequence crossed the Tehuantepec Ridge. Here in this segment, we see these two parallel structures, this cluster here and this cluster here. So it seems that there may be two parallel faults moving. In this segment, we have a change to mostly activity in the upper plate. And then this cluster here is, again, very interesting, but we haven't quite figured out what it's doing yet. And the mechanisms are also very complex. We have the main shock is a steeply dipping normal fault. We have intermediate depth normal faults, shallow thrust, shallow normal faults, all acting together. And so I'm going to quickly show here two plots trying to understand why is this earthquake occurring there. And so here we see the curvature of the plate in colors. So here is positive curvature and negative curvature. And it seems that these earthquakes are occurring somehow where there is the largest curvature. We also calculated the Coulomb failure stress, and it seems on this curved fault plane above the vertical normal fault. And so this is Coulomb failure stress on the megathrust. And so what we see is that effectively above the earthquake, above the fault, we have positive or an increase in stress, but on each side there is a decrease in stress, suggesting that maybe, at least for this part of the megathrust, we are decreasing the stress, and so hopefully there will be an even longer time till the next big earthquake on the megathrust than we thought. And so what is going on here? Well, there are now we have three of these large normal faulting events within the slab in the slab that's under the overriding plate. So now not in the outer rise like in most other regions, but more inland. And so there was the 1931 earthquake, 1999, and 2017 earthquakes all in this region. And so somehow it looks like there is some kind of slab disintegration event occurring in this zone. And so to conclude, the Tehuantepec earthquake was large but compact. It has a maximum slip of maybe 15 meters, rupture area of 60 by 40, and a rupture velocity of 4 kilometers. The earthquake broke through the slab, but probably not into the overriding plate. Aftershocks suggest rupture on parallel near vertical faults, as well as distributed deformation in the overriding plate. Coulomb failure stress modeling indicates perhaps diminished stress on the megathrust interface. And so finally, we are left with the question whether the large normal faulting events suggest a coupled interface in the Tehuantepec gap. And I would like to conclude by just thanking AGU, because many of us that are presenting in this session, we got special funding from AGU to come here, and we're very grateful. Thank you, guys.
We have plenty of time for questions.
Back in 1991, Stu Dushenko published what I think is a magnificent paper describing the seismic gap theory around the Pacific. And he used a diagram very much like the first one that you showed, showing the historic ruptures and gap. I hope you, or someone in this group, will follow what Dushenko did and make a testable hypothesis about the effectiveness of the gaps, because you've got all the same data, and obviously using that same idea.
Yeah, so I mean, a gap is sort of difficult to deal with, because if you have a gap, you can have two really end members of the seismic spectrum that can both explain the gap. Either that is fully coupled, it's so coupled that it hasn't moved for a long time, and you will have a giant destructive earthquake. Or the complete opposite, that is happily creeping, is not accumulating strain, and so you will never have an earthquake there. And so I think that's what you're referring to, that the gap theory is kind of dangerous in that sense, because it can mean completely opposite things. And so unless we have really measurements in these zones for example, GPS time series or something like that, that tells us whether we are accumulating strain, we cannot really distinguish between these two end members. So we are really excited to try to put some instruments in the Tehuantepec gap to see what is happening there. Is it creeping or is it locked?
Well, Nishenko had the same challenge, but he went the extra step to look at those places that were not apparently gaps, but had a history, and put probabilities on those too, so that you could use the whole ensemble as a test of the model. And I think it's a very important step, and it seems to me there's an opportunity right there.
Thank you. We'll look into that.
A super quick question. Yeah, Ross.
You're showing two parallel fractures or faulty events in the aftershocks. Are they simultaneous, or does the one a little farther inland occur a bit later?
A bit later. And so here, if we go back, you can sort of see the colors. So the blue colors are the first days after the earthquake, the first 2 days or so. And so these are mostly blue. And then here they start to be more into the yellow colors. And so that is occurring later. And also, like if you look in map view, they look more almost like a cluster. But again, these are relocations. So a lot of earthquakes have been thrown out. So that's not something that we can say just looking at this, that is more like a cluster, but it's certainly like an interesting feature that we have these two.
Thanks, Vala. Okay, we're going to move on. Want to introduce the next one?
You're standing over there.
Okay.
It's up there on the podium.
Our next speaker is Maria Teresa Ramirez-Herrera. She will talk about physical observations of the tsunami during the Tehuantepec earthquake.
Thank you. Good morning, everybody. So I'm going to talk about the tsunami that was produced by the September 8, 2017 Tehuantepec earthquake. And this was work by a group, UNAM colleagues, Angel Ruiz and Jorge Zavala, a colleague from CONACYT, Nestor Corona, and Diego Melgar at University of Oregon. I also want to acknowledge funding by UNAM and also personal funding. So the topics, basically what I'm going to talk is about what was the motivation for doing a post-tsunami survey in this area. And Vala already introduced nicely about the main event, but I just briefly summarize. And I'm going to just show you how we surveyed the tsunami, which data did we use, and some closing remarks on the results that we found. So the main motivation for going to the field and surveying a tsunami after this event, the first question we asked ourselves was there a tsunami? Because initially there was no information at all on a tsunami produced by this event. And then we wondered, was this a destructive tsunami or not? And the question was because normally, the earthquake was so bad that the media focused on the earthquake. The same happened in 1985, that also there was a tsunami, but most of the media focused on the earthquake. So we also wanted to observe and document all the tsunami effects, also asking people, local people, and also collect as quickly as possible any data before it disappeared, because it was a rainy season in Mexico. And then, so also we wanted to learn and also improve in general with our data, any research and planning, mitigation and preparedness in the local area. So the method that we used was, We use a preliminary earthquake source and a preliminary tsunami model, also produced by the colleagues of our team. We use also tide gauge data, arrive to the location, and talk also to the locals at site, asking them of their experience and observations. And we measure on size with using the preliminary tsunami model. We focus on those areas that we knew based on the model that had the maximum wave heights. And then we followed basically the IOC post-tsunami survey protocol and previous field experience after working on tsunamis. And then basically what we used was very simple, measuring in runoff inundation distances with an RTK GPS and a Sokia A40 level. And because some of the areas were hard to get into, we use also drones. And so that also helped us to expedite the survey in the field. So Vala already introduced to us, but I want to show you what we use. We use a preliminary earthquake source model produced by Diego, our colleague, and basically we knew the slip was close to 15 meters. We use also data from this Mexican seismological survey, and so we knew we had data on the rupture and where the epicenter was, and also we knew this was a deep event on a normal fault. So after producing the preliminary tsunami model, we found that these sites were the ones that had, according to the model, the maximum wave amplitudes, and that's why in this figure you see all these dots here focused. We did focus in these areas because that's where we expected the maximum tsunami waves and to find any evidence in the field. So here I'm gonna show you just what we used to trace the tsunami in the field. Because it was a huge tsunami, and also I want to point out that the Chiapas coast is not that highly populated, so we don't have so many buildings to measure the tsunami runoff, but we use evidence like natural evidence, like here you can see grass that was buried by a tsunami deposit, sand, mainly made of sand. And over here you can see, maybe it's tiny, but you can see that the grass has the direction of the flow of the tsunami, basically going to the north. So I put the compass, but it's too small. But I added here an arrow, and we found evidence of this area is covered by mangroves, and there are several lagoons. So you can see the mangroves were broken and branches like this. So we use these ones also to measure the runoff in the field. And before that one, and then with the drone, we had like access to this kind of areas where you can, maybe you cannot see, but I can tell you that this area has grasses that are already like dying, like yellow, and the reason why is because of the high salinity. So this was the area that was covered with the tsunami inundation, and we used these traces, these grasses that were already dying, to determine the distance of the inundation and the flow. And there are other kind of also features, interesting features that we associated with tsunami, that we found a tsunami kind of a fan behind this area. So, and then on fences like this, we could see the height of the water that was stagnated, but we also, you can see, notice the difference of the level of the sand over here and over here. So this was the sand transported by the tsunami. And so over here you can see mangrove trees that were transported also by the tsunami, broken, and huge trunks also lying on the sea. We talked to the locals, and this is close to a house, and they indicated to us, I mean, they had here a pole, and they told us that how high was the beach before the tsunami, and they indicated also there was all this sand transported during the tsunami. And you can see there is a sharp basalt contact in between what was before the beach, the previous beach, and the tsunami deposit over here that had kind of nice laminations. And over here you can see mangrove trees covered with sand produced also or transported by the tsunami. So we found also houses that, I mean, this is the grass of a little garden in a house that was covered with sand. And again, the grass, you can see that it has is showing the flow direction, and this house has some damage. You can see debris here of the house that was partially collapsed. Over here, there is another house, and the swimming pool was already with seawater, and no need to go to the sea. And then over here, you can see the mark of the runoff that we use also to determine the runoff height, and also the runoff inundation distances. We also record some of the earthquake damage in Chiapas that was not as bad as in Oaxaca state. I mean, in Oaxaca, the Tehuantepec has had more damage produced by the earthquake, but not by the tsunami. And we also record some of the geological observations like ground failure, landslides, liquefaction, and ground cracking close to the area. And here are the results of what we found. What you see in colors from greenish to reddish is the model maximum tsunami amplitude at the coast. And that's what we use to go to the field, and we try to focus in this area that had the maximum model amplitudes. And those were close to between the longitudes 94 and 93.5. So when we, before also going to the field, we use the TIGOCH data. And you can see here that the mariograms show the time of the earthquake. That's at Puerto Chiapas over here. And this one in Salina Cruz over here, we had the time. And also notice that the perturbations of the sea they lasted long, about 48 hours. So the sea was perturbated for a long time. And what is also interesting here, looking at the mariograms, is the time that took to the maximum amplitude wave height to get, I mean, it was like GMT time just before 6 o'clock, and over here is about 5 hours later. So this is very important in terms of tsunami mitigation and tsunami preparedness. So what we found also, just basically summarizing here, is that it was really nice to have the tsunami model because our results in general, like the post-tsunami survey, show that the amplitudes, the runoff coincide nicely with the maximum modeled amplitudes, and the maximum was about 3.5 meters. Also, we noticed we measured the inundation distance. It wasn't that big, 200 meters, but this is important also for us that are working with tsunami deposits and differentiated storms from tsunami deposits. So this is very helpful information. So just summarizing, we measure a maximum runoff about 3 meters at Boca del Cielo. The maximum inundation distance was close to 200 meters, just as next to, in that area close to the epicenter. And also we found that the preliminary tsunami model was really helpful. And finally, the tsunami, although it wasn't that damaging, it produced scour and erosion on the coast of Chiapas. And we learned from the tsunami deposits how much they went inland, like 170 meters, and the thickness of the tsunami deposits. Something I want to quickly say before my time is over is that there is a Mexican tsunami early warning system, and the system issues several warnings, but the tsunami arrival struck Chiapas coast prior to any official warning, and the reason why is because the early warning tsunami system in Mexico goes through several ranking notifications, and this really slows the message to the people. So this is something we have to learn and work on a tsunami early warning system that goes directly to the people and quick. So some people did not evacuate. Also, that's something very important. I mean, the earthquake was strong enough for them to notice that this was a big earthquake, but they did not evacuate. So we have to work hard on community-based education and awareness programs. So I think, am I running over, or I have a minute? So what I want just to summarize is that this was, in a way, not expected, as Vala indicated, earthquake, and also not expected tsunami. We tested the rapid response from the tsunami modeling that was produced, Diego, in very quick. So, and we also learn and understand more about the signature of currents, the current tsunamis to evaluate other areas in Mexico, like the Guerrero Gap, where we are expecting another big earthquake. And we also evaluated the effectiveness of the tsunami early warning in Mexico, and I'm not tired to emphasize that this is important to get to the people. We all do this for the people, right? I mean, not only for publications. So I think I'm not trying to emphasize that people need to get the warning. So thank you guys so much, and I want to also acknowledge help by students, UNAM students in Mexico.
We're going to move on, but this helps as a reminder that there's a poster session after lunch. Our next speaker will be Lingsen Meng. He will be talking about nucleation and kinematic rupture of the Tehuantepec earthquake.
Good morning, and thank you very much. Vala did a great job about the general picture of this earthquake, so I don't have to go through the tectonic settings. So I will talk about a kind of rapid report by our group at UCLA through collaboration with Luis Antonio Dominguez at UNAM about the fault shocks and the kinematic rupture process of the main shock. So I guess I'll probably just skip the overview. So let's just dive into the data. So we use a very popular approach, try to get more events than the routine necessary catalog. So it's a match filter template matching. We have about 60 days of continuous data recorded by 7 regional stations. What we identified here is that, if you can see, this is the identified events, and this is the cumulative number of events. And during the last day, one of the template, I'm pointing for 6 events, matched about a dozen of magnitude, high magnitude 7 or magnitude 4 events. And those occur just about a day leading up to the main shock. And if you look at the beta statistics on the map, you can see this is for the last day. We've seen a significant increase of the beta value, which indicating a acceleration of the productivity within about 30 kilometers from the main shock epicenter.
I'm sorry, could you go back? You're saying the foreshock squares?
No, this is the red dots here. So that's just right close to the epicenter. Yeah. So we have visually identified these fault shocks just to confirm they are true. And this is the template, and these are the detections. So you can see the P and S wave clearly. I mean, the detection has a lower signal ratio, but I think these are real earthquakes. So then we try to move on to get the source properties for the starting from the template event. So we use a generalized cut and paste method to get both the focal mechanisms and the focal depths. So the source mechanism is just very similar to the main shock. It's a steep deeping normal event, and focal depth is about 40 kilometers, which is about 10 kilometers above the SSN focal depth of the main shock. So we try to get a better location for this event as well. So we did a master event location of this fault shock with respect to the main shock hypocenter based on the arrival times in the local data. And here you can see the cross section. So this earthquake is about 20 kilometers up dip from the epicenter of the main shock. And if you just feed the fault lines through these two earthquakes, they aligned with the deep angle of the focal mechanism very nicely. So here we can probably say that they occur on the same fault plane, this fault shock and main shock. So this is maybe something less certain. So we also try to get the location for all those a dozen of fault shocks following the 4.6. So there are only 3 stations that we have confidence to extract the differential travel times with respect to templates. We did a relative relocation. I guess the location may not be accurate because the network is not really favorable, but we think the relative locations of these events are within about 2 kilometers from the template location. So that means that you are probably looking at the aftershock sequence of this template event. Okay, so what does these things say about the mechanisms for the fault shocks, how they lead up to the main shock? If you just assume a typical stress shock of 3 megapascals, this 4.6 is probably just 1 kilometer wide. And since the main shock and the fault shock distance are much further away, maybe the static stress transfer is not large enough to reach that. There's any alternative possibilities? I mean, there could be some like background stuff going on, could be a large-scale slow slip or fluid migration. But again, we don't see this migration of the seismicity. So it doesn't really support either cascade triggering or migrating slow slip. So could be that there are a lot of smaller events that we cannot detect with our available data. And the other possibility is that maybe we're seeing delayed dynamic triggering from this 4.6 to the main shock. Because if you just calculate the expected dynamic stress of this event at the hypocenter of the main shock, you get about 70 kilopascals. So that's reasonably large, consider that we have seen that events being triggered just by 10 kilopascals. So this is certainly a possibility. So then we move on to the main shock, and we use this popular approach, teleseismic back-projection, to extract the kinematic rupture process. Here we're looking at the stations in Alaska, which is within the range teleseismic distance. There's about 270 stations that we eventually use. And here are the seismograms. You can see clear, coherent arrivals within 60 seconds after the initial P waves. Okay, so one thing we do a little bit differently, we developed in recent years, is a slowness correction aimed to improve the accuracy of the back projection method. Like a traditional back projections using 1D velocity model, the 3D doesn't really help because we just don't know the velocity structure at high frequency, about 1 hertz, very well. So in the standard back projections, there's a static correction at the hypocenter. It means that if you see some errors of travel times at the hypocenter, we apply the same correction to the entire earthquake to account for the 3D structures. So as you could probably imagine, that's going to work if the earthquake is small and confined near the hypocenter. But if you move away as the earthquake grows, that assumption probably going to break down. So what we do here is that in addition to the static correction, we also add additional correction on the spatial derivative of the travel time at the source side. So it's kind of like if you look at an aftershock occurred away from the hypocenter, we also kind of make a correction for that. And this is kind of what it does to this specific earthquake sequences. We're looking at 8 large aftershock here. And so we actually relocate them using the local network. And like these stars are what you can find them in the SSN catalog. And this triangle are the back projection inferred location. Right, so like this is without the calibration, and you can see there are some biases, especially for those further away from the hypocenter. So after the calibration, after we introduce this slowness calibration, these things like collapse nicely at the same location. It means that we have reduced the location error to a factor of 3. Okay, all right, so then what does this leaves us to the kinematic rupture process of the main shock? I mean, this is kind of a map view of the high frequency radiations. So you can clearly see this linear trend, and it goes beyond the surface extension of the Tehuantepec ridge here. So it means like this fault probably goes beyond the ridge here. And we can also compute the rupture speed. I mean, the gray is the before the calibration, and the color ones are after the calibration. So if you have a trend, then you get the rupture speed. And the speed we get is about 3.5 kilometers per second. So you would think this is very fast, but if you consider this is a deep event, and the ambient shear wave speed is about 4.5 kilometers per second. So you're getting about 80% of the local shear wave speed. So that's a comfortable rupture speed, like most 3 rupture can operate for a sustained and stable case. And the other feature here is that towards the end of the rupture, we see that there's some additional radiations kind of stepped over towards to the north. So that's a very interesting feature over there. And this step over distance is about 40 kilometers. So that's pretty large, right? I mean, like in typical continental settings, like in California, this step over is probably not more than 5 kilometers. And the recent paper by Bai and Arturo, they conduct dynamic simulations, and they argue that if the seismogenic width is really large, the dynamic stress will be able to reach further and give us a larger crossover distance. And so here, if we look at the M8.2 main shock, these are a few published models. So they differ in the centroid depths because probably they use different hypocenter depths. But the rupture widths here are consistently larger than 25 kilometers. So that really make the case that this is a rather large seismogenic width, much larger than the 10-kilometer seismogenic width in California. So that's probably we have this wide step over in this particular case. And this is also what Vala mentions, that this is likely to be a reactivation of the subducted authorized normal faulting. So we actually surveyed the areas and mapped all these bathymetry fault fabrics on the authorized. And here, this is just a statistics of the length of the fault per unit area. This is the density of the fault along this Mexican or Central America subduction zones. And this black line here really sees that you see a peak of this fault density around the location of the 8.2 event. So that's really kind of support the idea that if you have a more supply of these normal faulting, you probably get a larger one. And we also look at the orientation of these faults, so that these dots are the orientation, the strike angles of the main shock and aftershock sequences, and this black line is the strike of the faults along the trench. So like you really see correspondence over there too, so this is really the supporting evidence for reactivation. Okay, all right, I'll leave my summary page here, and I'm happy to take questions.
Questions? Kelin?
Yeah, how does the most productive template compare with the waveform of the main shock?
Oh, you mean the correlation, the template of the main shock?
No, the template that's
Oh.
most productive in producing the foreshocks.
Uh-huh.
How does that compare with
Oh, right. Yeah, well,
the main shock?
yeah, the main shock has this finite source effect, so it's the waveforms are much more complicated. But we were able to do a cross correlation and do a relative earthquake relocation. So in terms of the arrival times of the template and the main shock, they are pretty similar. They're just like 20 kilometers away apart. Yeah.
One more? Okay, I have a question.
Yes.
Why does more density of outer rise fabric mean a bigger event?
Right, that's a very good question. So you would probably think it should be the largest or the dimension of those outer rise faults. But like on the bathymetry, there is sometimes it's very fragmented. So we think like a density of the fault is kind of a more general feature you can extract on the bathymetry. And like if you have like the density is higher, it's likely you're also going to have maybe a continuous or a connection of multiple these normal faulting over there too. Yeah.
Okay, one more? No takers? Okay, we're gonna move on. Thank you, Lingsen.
Yeah. Thank you.
Okay, our next speaker will be Shinji Toda, and he will talk about the September earthquakes, a chain reaction or coincidence, and what's next.
Okay, thank you. 3 destructive earthquakes hit southern Mexico only within 16 days. So the question is, did they occur as a chain reaction or coincidence? And then what could happen next? So that's the question. And let me show you the map first. So here is the sequence of these 3 shocks. This is the first one is a Chiapas earthquake. Well, I should have called it Tehuantepec earthquake, sorry. And then second one is Puebla. And then third one is I call Oaxaca earthquake. And the answer that we have is that the first one probably had no effect on the second one, but the first one just influenced the third one. And then we would expect another large earthquake possibly in the next year. So that's I'd like to present. And also, as the previous author's presentation just suggested, these are just intraslab events. And then also, these guys are deep intraslab events. So first, I'd like to just introduce that the first Chiapas earthquake just transferred the stress to the Oaxaca epicenter, hypocenter. So the first, let me show you the Coulomb stress transfer due to the first main shock to the hypocenter of Oaxaca. And this is a typical Coulomb map. And we resolve the stress onto this nodal plane for the Oaxaca earthquake if we assume this hypocenter is very shallow, as the USGS determined. And you can see that now the star, the hypocenter is in the red zone. That means this guy is was triggered by, could have been triggered by the first one event. But UNAM just located that the Oaxaca earthquake was relatively shallow, deep, very deep. It's 75 kilometers, but still in the red zone. So this is just a rough estimate. We can say that the first one triggered the third one as one of the awful aftershocks. But the difficult thing is just the second one is very far from the first Chiapas event. I think that the 600 kilometer northwest from here. And so we resolved the Coulomb stress onto the nodal plane of the Puebla, the second one. But you can see this is located almost white, almost white. And so that means the stress change is really tiny. I mean, it's actually 0.2 kilopascal, which is far below the tidal stress. So that means probably no relation between them in terms of statistical stress transfer. But that this second earthquake occurred in the transition zone between the flat slab and dipping slab. And the reason we have this kind of contrast is just background seismicity. I'm going to superimpose the seismicity here. And now it's color-coded by the depth, hypocenter depth. And you can see that, these seismicity is just very straightforward, just occurring along the dipping slab. But we will expect some kind of discontinuity here. And then could be a product of the flat slab. And so one could just expect the tear slab of the subducting ingoing slab, and that could also separate the western part of flat slab from the simply dipping slab. So, and then, but the seismologists probably argue that the dynamic stress change caused by first one, which probably has a directivity to the northwest, influenced this area and could trigger the second event. So, well, to prove that, we just examined the seismicity near the Puebla epicenter. And let me show you that. So this is the cumulative number of earthquakes near the hypocenter of the Puebla second event. And, but we don't see any evidence of triggered small events between the period between the Chiapas and the Puebla. So what means that we don't have any increased seismicity due to the passage of the seismic wave. Well, and then so that means that so could there be coincidence? So that's a question. So to calculate such probability that two events occurred within 11 days, so we first employed the GEA model, which stands for the Global Earthquake Activity Rate Model, which actually furnished us the 0.5 annual % for both events for their locations. But next we have to calculate exactly the probability that these two occurred in 11 days using these numbers. So to do that, we actually used the birthday paradox equation. So let me explain that. My birthday is December 10th. So is anybody just who has a birthday, the same birthday with me? No? Wow, this is really a rare case. But, but normally that the probability is much higher than we expected. So in this case, there are only two students, Chiapas and Puebla, and they are like a 600 kilometer wide classroom like this. And that gave us a number of a chance in 200. So this is actually rare, but not super rare. So compared to that, we also calculated the probability for the second earthquake actually happened to hit that the 2 hours within the annual earthquake drill because it happened to be same day 22nd anniversary of the Great Mexican Earthquake. So that actually gave us a chance almost in a million. So you can compare these numbers. So that means that the sequence of Chiapas and the Puebla is more likely than the, yeah, so that one. So that's the message. Well, these are accidents probably, but actually we had 2 large earthquakes. So probably that raised the local seismicity, which means that raised the seismic hazard temporarily. So, so what could happen? So here is the map that the first speaker presented. And we had the 2 seismic gaps, Guerrero and Chiapas. And fortunately, Guerrero Gap is very far from the Chiapas and also from the Puebla. And so as we expected, because of the distance from the source, we don't see any significant seismicity rate increase after the first event in Guerrero Gap. So you can see this is yellow or white. This is within the error, I mean uncertainty. But you can see that there are widely red area very close to the Chiapas source, and especially the northwest part beyond the edge of the source. And if you look at the deeper seismicity, mostly composed of the normal faulting event along the slab, we could also see the very high rate increase in this region. And we can see modest increase near the area. But these are observations. So that means that we cannot simply apply this one for our forecast. So that means we built a model using rate and state friction together with our calculated Coulomb stress change. So here is the model result. This is just a color pattern indicate the expected number of earthquakes that the cumulative expected number of earthquakes until November 22nd, when we download the catalog, and since the main shock. So we expect a lot of aftershocks in the redder regions. And what happened? So the majority of the aftershocks match to the red zone. And how about deeper intraslab events? So here now the red zone shift to the inland, to north. And also these, the aftershocks just match the red zone, roughly. So that means that this kind of a model have some power to forecast the future events. Especially, this is just for the small shock down to magnitude 4, but we could extend to the magnitude 7 using Gutenberg-Richter relation with the b-value equal 1. And so let me show you the results. So this is just a table of the result. And then this is the combination of assumption of the Dietrich parameters. And this guy is just a probability for next year without any effect of large earthquakes. And the remains are just increased probability because of the stress transfer by the recent 2 events, mostly the Chiapas earthquakes. So that means you can see that 50 to 100% probability gain associated with the stress transfer. So let me summarize my talk by saying that even though that the Chiapas and Puebla sequences could have been an accident, we could say another large earthquake would occur by a chance of 30 to 55% in the next year. Thank you very much.
Questions?
If you just compare the background rate
Mm-hmm.
in the area of the 7.1
Mm-hmm.
to the ETOS rate predicted from magnitude 8,
Mm-hmm.
assuming a power law distance decay, with just the empirical decay that you measure, you get that they're the same order of magnitude. So I don't know if I agree.
Oh, you mean that,
but they're
well,
roughly the same number. And
yeah.
the fact that it's a 7 has nothing to do with it because both aftershocks and background energy are distributed.
Okay. We use,
Could you repeat the question, please?
Okay, so it's difficult for me to repeat. But anyway, she just used the ETAT model with the distant decay, right? So it has almost the same number?
Yeah, it's roughly the
Oh, sorry.
Just a back of the envelope calculation, and ETOS gives the same. The ETOS rate at the location of 7.1 is about the same order of magnitude as the background rate where the 7.1 occurred.
So,
I don't know what you mean.
So-
if you take the ETOS rate predicted from an 8.1, that many kilometers away, parallel to 60K, given its size, you can predict the rate at that point where the 7.1 occurred. You can just
Yeah,
compare
but-
that to the background rate.
you get a very small number, right?
But there are no earthquakes in that zone after the.
Yeah, that point we made it just, sorry.
But compare that to the like the background rate of a 3, you reduce it by the same amount compared to a 7 by doing the aftershock calculation and background calculation. So exactly the 7, that doesn't matter. What's the chance of an earthquake of a given size being triggered versus the background rate of a given size versus triggered? Just compare those.
Okay, thank you for your comment. Yeah, we should do that. Yeah. Well, but the point we made is just we didn't observe any small shocks triggered by the dynamic wave. Well, it depends on the detectability issue, right?
Any more questions?
I think you could adapt the birthday probability model to the probability of a gap along that tectonic boundary with a little bit of weighting for the size of the areas affected by previous earthquakes. Have you thought about that? That maybe these gaps?
No, I haven't thought about it. But that's a good idea. So we should do that. Thank you, David.
Okay, we're going to move on. Our next speaker will be Arturo Iglesias, and he will talk about kinematic source inversion for the second earthquake, the Puebla Morelos earthquake. Arturo?
Thank you very much. Well, as Vala mentioned before, actually this work is by a bunch of authors, so maybe it's better to call UNAM seismology group. And here in this picture, you can see you can see a monument called Monument to the Mother in Mexico City. This monument was built in 1964, and after 1964, it had resisted a lot of earthquakes, including the 1985 Michoacan earthquake. However, in this 2017 September 19th earthquake, monument collapsed. Just as a comment in the previous talk, what's the probability that we had in Mexico City 2 disasters earthquake in the same day? So I'm not sure if Alan compute that probability. Yes, I think so. But this fact suggests that in Mexico City, the intensities of this recent earthquake were worse than previous one, at least in some parts of the city. Victor Cruz is going to talk about the regional effects and site effects, and to try to explain that. Again, this figure from Costoglodo Pacheco and Pacheco, you can see here the largest earthquakes in actually the last century. So this is the 1932 8.2 earthquake, and largest earthquakes occurs here at the collision part between the Cocos Plate and the North American Plate. However, you can see these earthquakes located in the subducted Cocos Plate, and I show you here in the global CMT catalog this section, these earthquakes located in almost east-west or west-east in this section. Our earthquake now is located here with the red symbol, and you can see two characteristics. One is maybe the closest earthquakes, at least from this magnitude, to Mexico City, and the other characteristic is as large as the largest than we recorded before, 7.1. So this position and the magnitude explains the effects in Mexico City and other important cities in central Mexico. So using this section from Victor, you can see here the position where the subduction earthquakes occurs. This is the Cocos Plate subducted. As you probably know, we have a flat subduction for about 100 kilometers from some point here. And we think that this earthquake occurs just where the plates bending again and sink into the mantle. So in the section, as a cartoon, this is the position of the earthquake. We compute the regional moment tensor solution using Draeger approximation, and we use these stations, data from these stations, regional stations. These stations are part from the Mexican Seismological Service from Institute of Geophysics of UNAM. And here are the feeds and the obtained focal mechanism. The mechanisms are quite similar to the obtained by Global CMT using teleseismic data. And fault planes are really very similar, and the scalar moment is also in the same range. So after the 36 hours, more or less, the technical staff of the Institute of Geophysics installed 3 portable stations, broadband stations, 3-component broadband stations, very close to the epicentral area. We had data also from another station from a previous experiment, GGAP, and we have also data from the stations from the National Seismological Service. This earthquake provoked just a few aftershocks, a very short sequence of aftershock, but we could catch some of them here inside this box, and if we plot the section A prime, we obtain a section like this. This is the 45 degrees from the empty solution, and well, now we think that the fault plane is the fault plane which deep toward northeast. So one of the important questions is from the both planes, from the solution, from the empty solution, which is the fault plane. Actually, we made the kinematic inversion for both planes, and the solutions in terms of the feeds are very similar, so these aftershocks are very useful to distinguish the fault plane. So to obtain a kinematic approximation, we use data from these stations, Institute of Engineering stations, blue ones, and Geophysics Institute stations, the Seismological Service Network, here show it. Okay, I will show you some records from these stations located southeast from the epicentral position. And you can see here the accelerograms, the strong motion records from this station. And you can distinguish these 2 pulses in the records, in the strong motion records. And after 2 numerical integrations, you can obtain this signal with the 2 pulses separated by around 5 or 6 seconds. In the opposite direction, in this station, I can show you the signal or strong motion record is more complex. However, you can also distinguish these 2 pulses, maybe here, but after integration, actually, the result is complex. So we use this fault plane, a small fault plane, but divided in 10 by 10 subfaults. Each subfault has 3 kilometers in each size. So, and we use frequency domain inversion technique proposed by originally by Cotona and Campillo in 1995, and we obtained this sleep amplitude pattern. We of course use the fault plane which deep to the northeast. So you can see here the position of the hypocenter. This is the top of the fault plane. This is northwest direction. I have another figure to understand better. But you can see here the nucleation point. We have a large patch here, and some seconds after this patch, we obtain this another rupture, and then 7 seconds or so after the initiation point, we obtain the largest slip over the fault plane just at the end of this fault. Rupture times are close to constant rupture velocity, but not here in this position. So here maybe is better to understand. So hypocenter is here, and you can see sometime later some asperity here, and sometime later, like 7 seconds, 6 or 7 seconds, we have large displacement in this region. So, well, maybe this displacement could explain the effects also in Mexico City. I mean, like a directivity effect. These are the fits. We can improve the fits, of course. In this approximation, we use fixed rake direction. So maybe we can let the program find the right rake direction. So this is the teleseismic inversion, and of course it's more simple than before. It's a 7.1 earthquake. Maybe it's the limit of the method. But you can see some similar. So the hypocenter is here, and propagation is in this direction. It's the same direction, the strike direction, and some displacement in this edge of the fault. So this is another method, of course. So as a summary, we obtained the regional moment tensor, and the regional moment tensor is consistent with the reported by global CMT. I think important conclusion of this work is that the preliminary aftershock analysis showed that the fault plane is the fault plane which dips to the northeast direction. And well, the slip distribution over the fault plane is characterized with a patch close to the hypocenter and something similar to a semicircular rupture 5 or 7 seconds after the initial time. And that's it. Thank you very much. 8 seconds before.
Questions? I have a question, Arturo.
Mm-hmm.
So your fault seems to rupture inside of the slab, so that would suggest it seems to break down into the part that you would expect to be in compression because of the bending. Is that true?
Normal focal mechanism indicates
Right.
tension.
Yes.
And well, In the top of the slab, we expect tension. Yeah, but yeah, if the rupture propagates down deep, I'm not sure what's that.
Another question, Arturo.
Welcome.
These two pulses you detect,
Yeah.
they correspond maybe to the trigger and the stop phases, or have you made a kind of analysis?
Well, actually, it's just a kinematic approximation, so it's, in the method it's not solved that, but yeah, of course, probably would be Paco. So I know Victor's students is working with dynamic inversion, so I think he can resolve very soon this part.
But the stress drop was about?
The
stress drop, you have an idea?
No, at this moment, Paco, but I can tell you later.
One more question?
Seismic moment scalar is well solved, of course, but the stress up, I don't have no.
I can ask a question.
Yeah.
So on your inversion, the first one, you show that the second pulse is kind of in the corner. Have you actually tried to expand the box at all to see if you can get the full edge, because it's clearly sitting right at the edge of your box? Have you tried to expand the box?
I tried, and fits are better, but the sleep is not so soft, so there is a trade-off to choose the reliable solution and the fits. But yeah, I tried.
Okay.
Yeah.
All right, we're going to move on.
Thank you.
Arturo. Oh, that was the mouse pad. Hmm? Oh. Am I jumping the gun here? Oh yeah, we're out of order. Are you sure, Alan?
Yeah, we changed it.
Okay.
Yeah.
All right. Okay. Our next speaker will be Dario Solano Rojas. He will talk about remotely triggered slip induced by the September Puebla earthquake. Dario?
Hi everyone, my name is Dario Solano. I come from University of Miami, and yeah, I'm gonna talk about the slip induced in Mexico City by the Puebla earthquake. And I wanna thank my co-authors, Emre Habasli, who is back there, and Shimon Udowinski, who is over there, and Enrique Cabral, who couldn't make it this year to you. But yeah, so why is this work relevant? Well, during the 2017 Puebla earthquake, there was a lot of damage in the western part of the city, of Mexico City. Several building collapses, around 30 buildings collapsed, 200 deaths in total in Mexico City. But that happened in the west. In the south, there was a different kind of damage, which was also very destructive. But you know, not a lot of buildings collapsed. So it was different, but there was a lot of shallow faulting in the southern part of the city. So what we're presenting today is you know, a contribution for the understanding of what happened in the southern part of the city. And the outline of this presentation is a quick introduction, then we want to talk about what is INSAR, then the processing and the results we have, and the conclusions of the work. So, as you know, Mexico City is located in central Mexico, and is 100 kilometers away from the epicenter. But still, with these contours, we show the the shaking map from the USGS. And as you can see in the part of Mexico City, there is a very strong shaking. Do I have a cursor? Oh, okay. Okay, so Mexico City is over here, and the epicenter of the earthquake is over here. So if we zoom in a little bit more, it's the same contours, but now I have plotted on top of it all the damage reports from OpenStreetMap, which were collected by, by the public and mapping efforts independent of the government in the city. And you can see that there is some correlation in the space, but not a lot. But then we look at this zonation of the city. The city is divided into three geotechnical zones: the lake zone, the transition zone, and the hill zone. The hill zone is the stable zone of the area. The lake zone is a thick layer of clays, and the transition, well, is the transition zone between those two. And then we have the damage reports over here, no? And as you can see, they align pretty well with the transition zone. And we have over here the maximum ground acceleration with a period of 1 second, calculated by the Institute of Engineering in Mexico for the earthquake. And the black triangles are the buildings that collapsed in the city. So you can see that there is a good alignment with the transition zone and the maximum ground acceleration. But we're going to talk now about how to use INSAR, or what we can see from INSAR, to understand what happened in the southern part of the city. So INSAR works with the calculation of the difference of the phase of two SAR images, and then we can obtain these colorful maps that we call interferograms. And if we use several interferograms and perform a time series inversion, we can obtain a velocity map. In this case, this velocity map is showing the subsidence over Mexico City of around 330 millimeters per year in the eastern part. And then the area we're going to analyze is over here. No? This is called Sierra de Santa Catarina in the south. And then the reports of all the buildings that collapsed are over here. So it's kind of a different area we're looking at. So the data sets that we have to work with are one data set from the Cosmos SkyMed satellite constellation. These are X-band satellites, high resolution, 3-meter pixel resolution in space, from December 2011 to June 2012. And then we have 170 scenes from the Sentinel-1 and B satellites. But these SAR scenes are not as high resolution as the Cosmos SkyMed. The final resolution that we get is around 60 meters per pixel. And we have data from 2014 to 2017, and the earthquake happened over here in September 2017. But because we have a lot of Sentinel data, we can take also a subset and analyze it independently. So we're going to take a subset from September 5 to September 29, 2017, which also includes the earthquake. And also we can calculate just a single interferogram using only two SAR scenes, September 17 and September 29. So we are basically analyzing 3 velocity maps and 1 interferogram. This one over here is not related to the earthquake. This one includes the earthquake, but it's like just one scene of 170. So it's basically not doesn't make a lot of noise in the computation. And in these two, yeah, the earthquake has a lot of influence. So processing the first data set, the Cosmos SkyMed 1, we have this result of a velocity map. And then we want to decompose this subsidence signal into components based on the wavelength or the spatial frequencies of the subsidence signal. To do that, we first analyze the power spectrum of the subsidence signal in the frequency domain, and we take several profiles of this power spectrum that are the ones over here. We calculate the average, we calculate the best fit model, and then with this best fit model, which is the red line, we segment, segment the model, and we find a threshold of 500 meters, which is one of the thresholds we're going to use for the filter. And then we find a second threshold of 40 meters, and that is related to the construction of the metro system, which is a different talk I'm going to have later today. But what is important is to see that we are using 2 thresholds, 500 meters and 40 meters. So we take the subsidence signal, and we decompose it into 3 components: the low spatial frequency, the intermediate spatial frequency, and the high spatial frequency. The low spatial frequency is basically the regional subsidence. The intermediate spatial frequency is the local subsidence changes, and the high spatial frequency is the very localized signals of subsidence. And the ones that we care about are these, the local signals. No? So if we take these local signals over an area, like in this case Iztapalapa, we see that we have variations of the signal from -5 to 5 millimeters per year. And in the boundary of those variations is a zero, right? No change in subsidence. And if we run an edge detection filter, we can calculate the boundary of these residuals of the signal, no? Of these variations of subsidence. If we do exactly the same thing for all the area around Sierra de Santa Catarina, we obtain all these red polygons. These are the boundaries of the differential displacements detected by us using INSAR from 2011 to 2012, independent of the earthquake. And then we compare them with this map released by the Mexican government, which is all the faults mapped in the city, but in a period of 10 years. So with 6 months of INSAR data, we're getting a good approximation of where the faults are located. Of course, we cannot say these are faults because we are not sure there is a displacement that can classify it as faults, but it's differential displacements. So pay attention to this one, but because this is the one that we're going to use for our comparisons in the rest of the slides. Then we take the Sentinel data set and calculate the subsidence velocity for the period 2014-2017. And then we calculate the horizontal subsidence gradient according to Cabral-Cano et al. 2008. And we see that these areas in red, which are the high subsidence gradients, also have a good correlation with the results we get from Cosmos Skymed. And then these purple triangles are the locations we visited in the field, which also correspond to faults that formed during the earthquake. Then we take the velocity map from September 5 to September 29. These are 5 dates. And the results of this one are influenced a lot by the atmosphere, but still, if we zoom in a little bit here, we see that this square here, which is the Sierra Santa Catarina, have still some red spots in the north, in the south, and over here, which correspond to the results we found with Cosmos Skymed. And then we take the single interferogram, and this is very hard to interpret if you're not into INSAR a lot, but just let me tell you that this is displacement that happened during the earthquake, and also corresponds to the areas that we have detected previously. So the conclusion number one that we have from this analysis is that from Cosmos Skymed, there is movement in the differential displacements around Sierra Santa Catarina. Then from Sentinel, there is a long-term displacements or long-term differential displacement that is occurring in the same area. Then from this data set over here, there is differential displacement happening during the earthquake, and also in the interferogram level, we see displacements in the same area. No? So it is moving before, during, and after the earthquake. And the conclusion number two that we get from this analysis, this data set is the damage reports from the Mexican government. This is higher density. This in green you see slight damage, and in yellow you see uncertain risk, which means like I imagine more damage, but the government doesn't say it like that. And if you plot on top the results we got, we see a very good correlation between the yellow and the results we get from Cosmos Skymed, no? which are the displacements that are also happening during the earthquake. And so now for the western part of Mexico City, where there are tall buildings, we have that the influence of the maximum ground motion is what influence the collapses of the building. But in the southern part of the city, where the buildings are 1, 2, 3 stories, what is driving the damage is more related to the shallow faulting that we found. That's one of our suggestions after this work. Thank you.
So we have some time for questions.
So this is differential sediment, not tectonic fault, correct?
Yeah, right. They are faults because it's a surface plane, and then there is displacement in a parallel direction of the surface. But yeah, it's not a tectonic fault. Mm-hmm.
You have any other questions?
Are you comparing the amounts of displacements along the years, like the normal evolution, and what's happened close to the earthquake in terms of amplitudes? Can you do this with this data sets?
Well, we have what happened. Okay, the data set that we have like more information about is the Cosmos Skymet because it's very high spatial resolution. If you compare only that with what happened during the earthquake, and you go there and measure, it's the same locations, only that with the Cosmos Skymet you see displacements around 10 millimeters per year, and during the earthquake you see up to 1 meter of offset in the same areas. Yes.
You mentioned that in the western part it was mainly high buildings,
Mhm.
but my understanding is that there were also buildings in between 2 to 4 floors maximum that collapsed.
Yeah, right, and also in the south, but if you think of that as a general shaking, okay, that can happen anywhere, no? But most of the buildings that collapsed in the western part are higher than that. But still, the damage is dominated by high buildings collapsing. No?
Any other questions? Okay, Arturo?
This conclusion suggests that the distribution of the damage reports are related to the subsidence or to the fractures.
Yes.
Actually, I think it's not so correct that conclusion because I think that the distribution of the subsidence coincides with the transition zone, and the transition zone is related in this case with the damage the collapse of buildings. So I think
That is true for the western part of the city, but for the south it is not true. In the other analysis we have done previously, we can see that the transition zone is not matching very well the subsiding zone of the city. Mm-hmm.
Well, I think that question actually leads to our next talk very nicely. So we'll switch speakers now.
Thank you.
Thank you. So our next talk, it's already here. No, it's this one. So our next talk will be given by Victor Cruz, and he'll be talking about a physical model for Mexico City, the seismic response after the earthquake.
Thank you, Alan. Good morning. So far, the tectonic settings of both earthquakes have been already stated, so this makes things easier. In this talk, I would like to share with you some new results we have that pretend contributing something somehow to better understand why the damages during this earthquake were located where they were. So, excuse me, just to go forward. Okay. So just briefly, we have 3 different kinds of earthquakes in the whole country in Mexico. The most frequent are, as we all know, the typical thrust earthquakes just below the coast. Then we have this interest lab that are those who ruptured this year, which are less frequent, but recent works analyzing several records of those earthquakes in Mexico City show that the exceedance rate at the city from both kind of earthquakes are similar, which means that the seismic hazard from the probabilistic point of view is almost the same. So that's why this earthquake should now be considered more in detail by engineers to see whether the current building codes contemplate those solicitations coming from this earthquake. So Okay, so the earthquake that happened in September 19th occurred here, 7.1. We already saw some introductory ideas about it. I just want to point out something else. So it's an intermediate depth earthquake, just 114 kilometers southeast from Mexico. So it's one of the closest, probably the closest and largest to Mexico City of this kind. And 44 buildings collapsed in the city. More than 360 people died, from which more than 200 in the city. And the PGA in the hard rock, we'll see more in detail how the soil of the cities is done, was twice as large as the one recorded in 1985 during the devastating Michoacan earthquake. So when we felt that, I was not in Mexico, when people felt the motion, they knew, and I would have knew as well if I was been there, that it was something really extreme. So we haven't experienced something like that before, even for those who have lived the 1985 earthquake. Just to tell as well, so these earthquakes are very interesting, the intraslab earthquakes, because they are extremely energetic. The total energy change is large. But most interestingly is that the radiation efficiency of those earthquakes, this kind of earthquakes, is very, very low, is even lower than tsunami earthquakes, or kind of. So about 75% of the whole energy change remain in the focal region, and only with the rest of the energy that remains, that is radiated, is high enough to produce very large PGAs. So they are very, very interesting events with so these are it's a picture showing that where the damages were concentrated in the city. The colors here correspond to the dominant periods of the soil, and in the right, so these are the collapsed buildings, and to the right is the soil conditions, geotechnical soil conditions. So as has been said already, 3 different zones: the hard rock sites, which are mainly composed by lava flows; the lake bed zone, which are clays, very compressive clays saturated in water, and the transition zone with alluvial deposits. And most of the damage concentrated in this very narrow belt that follows the transition zone. So this earthquake has been recorded by more than 75 strong motion stations, most of them coming from the CIRES, Centro de Instrumentación y Registro Sísmico, and some other from the Institute of Geophysics. And so this is the result of the data they provide us. We thank a lot for this huge effort to have this very, very useful set of data. What we see here are the spectral accelerations, the response spectra average between 2 and 3 seconds. So here's the maximum value. I can read from here, but it's more than thank you. More than 400 gal. Thank you. And we don't see a very clear correlation between the damages, spatial correlation, and the maximum values of this metric that has been critical during the 1985 earthquake, where around 400 building collapsed, but much higher than those affected this time, that were 100% of them between 1 and 10 stories. So there's no a big correlation between the actual spectral accelerations between two. But if we look at shorter periods, between 1 and 2 seconds, we see a very, very nice correlation between these maxima and the place where the buildings are located. So what we tried to do was to better understand why this happened. So in this sense that the affected area during this earthquake was not the same, although there was an overlapping between the region affected during the 1985 earthquake that was mostly this region toward the downtown where the clays are thicker. There's a clear difference between two patterns. So let's just concentrate into this specific part where the strongest motions were recorded and see more in detail how they were, the recordings here. So we have a hill zone here record, and here's the champion station of the whole valley. We have in the east-west component spectral acceleration at 1.3 seconds that are higher than 1,000 gal, so about 1.2 Gs at 1.3 seconds, the spectral acceleration. So these are the geometric mean of the horizontal components versus the vertical. The point here, so here is the champion station. Compared with the hard rock, it's about a factor 10. In the maxima spectral acceleration, so in a very short distance. So it's a very complex pattern that can be also seen here from the particle motion polarization. While in the hard rock you see at the period where the strongest motion was recorded. While in the hard rock you have one single polarization. You see, for instance, in this station you have an initial polarization in that sense, and then it turns. So we have diffracted waves that are coming from the basing edges and that make the motion very complex. So there's a huge 3D effect of the whole basing if we want to explain what happened. So what we did was perform some numerical simulations using a platform we have developed during the last 10 years or more, Galerkin discontinuous approach that solves the elastodynamic equations with viscoelasticity, so that we can introduce very accurately the way Q varies with frequency. In this case, it's constant, but it's good enough for our purposes here. So here's the mesh, more than 27 million elements. We discretize a tomographic model, and we provide by Zach Spica et al. And we added the Trans-Mexican volcanic belt, and then the basing where the speed, the shape of the interfaces change within the space. So the thickness of the layers change and depend on the dominant periods of the, we have in the whole city, which are thousands of measurements. So we performed this simulation. So for that, we assume a stochastic kinematic source based on the previous inversions. I mean, it's a stochastic example. We don't care about details. We just want to produce a reasonable good radiated field. So here's the peak slip rate. So that's the final slip. So this is the comparison between displacement in the hard rock side, reference side we have at UNAM, between observed and synthetics below 1 Hertz. We see a nice agreement in low frequencies, but we still have a lack of accuracy for higher frequencies above 0.5 Hertz. So we are dealing with that, but we don't care for the purpose of, so far, for the purpose of this work, as we'll see next. So this is just to show a movie of a simulation. I don't know what to do. Ah, right, the mouse. Good. So this is a zoom of the simulation just in the basing. So the waves are traveling, then they arrive, and the first waves, and then the huge energy coming from southeast, from the epicenter. And we see very complex patterns here in some regions that we'll analyze next, that can better explain why the damage is concentrated where they happened. So the simulation, so just to tell you that the strong shaking duration from the area's intensity is about 3 times longer in the actual data, 3 times longer, about 1.5 minutes in the deep sediments than in CU that was just 30 seconds. Oh, I have to hurry up. So I'm almost finished. So this is a comparison between synthetic and observed spectral accelerations. So we have a factor 2. We are underestimating about a factor 2, but qualitatively it's very nice, the comparison. There's no correlation as we saw before with the damage. But if we look into 1 and 2 seconds, the comparison qualitatively still is reasonably well between data and synthetics. So what we did was to project these quantities into this section, in perpendicular section to the basin H, and that's what we have here. So the collapsed buildings in blue as a function of distance from the basin H. We have the spectral accelerations between 1 and 2 seconds observing continuous, and this continuous is the synthetic model. So just so the question is, what happens there in this region that promotes this very high amplification of seismic waves? So here I'm showing you the last slide, where we, from that simulation I just showed you, took a section here that we see here, the seismograms, and we clearly see these are the edges of the basin, and we clearly see how from the edges there's a fundamental mode, Rayleigh waves propagating very slowly. We have compared this with the theoretical dispersion curves from the model we used. And they are clearly dominating the fundamental mode, the motion close to the basin, within the 5 kilometers where we found the damages. So this is just as a reference, this is the PGA as compared with the hard rock size. So we have an amplification about 15. So that's the mechanism we believe has produced the damages in that specific region for that earthquake. So the damage is found. So that's what I said. I just led you my conclusions. And if you have probably questions, if there's time. Thank you.
So we have time for just one quick question.
Have you looked at the velocity of the observed data, not just the acceleration?
Yes, we have seen everything. Yes, from also the spectral velocities, the accelerations. Yes, right, and they are very similar. I mean, the comparison with the synthetics are very similar. Yeah, because they don't. There's a factor between the accelerations and but we can discuss because I have some doubts. Thank you.
Okay. So we're going to move to our last talk?
Sure, thank you, Ali.
So our last talk will be given by Kelin Wang, and he will be talking about the thermal, petrological, and structural conditions for the interslap earthquakes.
Thank you.
The pointer? Sorry, pointer. Oops, sorry, I already skipped your first slide.
Okay, as subducting slabs move down, the increase in pressure and temperature cause metamorphic reactions, and hydrous minerals will dehydrate, and the crustal metabasalt will be eventually transformed to eclogite in the mantle part of the slab. And if the mantle part was hydrated before subduction, and the minerals, hydrous minerals will break down as the temperature and pressure increases. And these reactions and associated dehydration and mechanical consequences and are thought to be responsible in some way for intraslab earthquakes. And depending on the age of the incoming slab, the pressure, temperature, or PT paths of the slab can be quite different. And there are warm slab subductions and cold slab subductions, and the earthquake behavior and is expected to be quite different between these different groups. The earthquakes in Mexico belong to the warm slab group. And they are quite similar to some other subduction zones. This is actually a previous earthquake also in Mexico, as mentioned in some of the previous talks. And also that's an earthquake in Nankai Trough, Japan, and that's a Cascadia. And these earthquakes are quite similar in some way, as you can see. They all rupture the mantle part of the slab, and but except this one, the recent one was quite large. And so we want to explore and what are the conditions, thermal, petrologic, and structural conditions for these kind of events. And an early, not too long after the squally earthquake in Cascadia, and we developed some thermal models for the Cascadia subduction zone here, and we're able to determine the actual rupture plane of that earthquake. It was determined to be that nearly vertical one, and it turned out, according to the model, the rupture was contained in the zone of serpentine stability, antiquarite, if water could go that deep into the slab and to form serpentine. And so, it happened, of course, it was a very warm subduction zone, and it happened after the basalt to eclogite transformation. And so we can do a similar exercise for Mexico, and the thermal modeling strategy is by now is quite mature. If you know the age of the incoming plate, we know the geometry of the slab, and even without good surface heat flow constraints, and we are fairly confident. We have a fair degree of confidence and about the results, the overall first order results. And this is the result for the one of our earthquakes here, the larger one here, and a thermal profile, and with the slab geometry taken from slab 1. Of course, that can be discussed we have better observations. And the results showed that if you use the USGS epicenter location, and the epicenter, hypocenter is at a temperature of about 600 degrees or a bit less. And there are also models of the rupture, and I think the USGS models are published quite early, and it's quite similar to some of models I saw this morning. And they all feature the rupture plane and roughly mostly above the hypocenter, but some models may go deeper. But in any case, the rupture involves most rupture has to be in the mantle part of the slab. And based on this morning I saw better aftershock locations based on those earlier plots, and it seems like that could be our rupture plane as assumed in the USGS rupture model and some other models I saw this morning. And so it perceivably, and the rupture plane would be something like that. And it ruptured mostly in the mantle part of the slab, and the crust was involved to some degree, and the rupture is mostly contained in the stability field of the antiquarite serpentine. So that's for one profile, and we can do this. And of course, I should mention there are different hypocenter locations, with some were published quite early, right after. There's a lot of uncertainties. But no matter what, and it is quite obvious, most of the rupture has to be in the mantle part of the slab. And we can do a similar exercise for the other profile and the other earthquake, and the geometry is more complicated, and the slab is a bit warmer. And in any case, if you use USGS hypocenter and the rupture is assumed to be this way, but it could be the other way, and that's up to discussion. No matter what, and the most rupture, a lot rupture seems to be in the mantle part of the slab as well. And according to some other later, maybe better defined hypocenter locations and rupture geometry, and seems like the hypocenter could be even deeper than that, more inside the slab, and instead of the lower crust, but probably in the mantle part. And then we have the question: what facilitates seismic faulting at these depths? And intraslab earthquakes or intermediate depth earthquakes require two conditions. One is there has to be enough differential stress to cause failure. And the second is the failure has to be in the form of seismic slip, high rate, localized slip. And the first condition is never an issue, right? There's enough stress, differential stress in the slab. And the problem is, and under that kind of confining pressure, even though the rock is brittle, how do we make localized seismic slip instead of cataclastic flow? So these two should not be confused. And so the question is really the second one. And the second one, and I triggered a lot of hypotheses, right? And maybe the most popular one is dehydration embrittlement. But we have a problem here. The problem is, at least for this one, as you can see, the temperature doesn't change with depth and very much in the slab. And if the serpentine dehydration is somewhat responsible for that condition, and the serpentine is not dehydrating at this depth range. So we do have a problem, and a better illustration is this. I show this one, right? It's a slab mantle metamorphism, and that's the dehydration boundary of antigerite. And I also showed for worm slab, it basically follows this kind of path. However, if you trace a point here deeper in the slab, here, in the incoming plate, we follow that one, and we'll see the PT path is actually like this. So that part of the mantle, if there's serpentine there, and it's really not dehydrating, and actually it's moving away from that dehydration boundary. So we do have a problem here. So problem is, it's difficult to anticipate dehydration to be responsible for this kind of earthquake. So there are different solutions, right? And one, the ready solution is probably no special hydrologic conditions are needed for this depth range. It's not that deep, and this paper recently published is quite important, I think. They actually observed pseudotachlite at similar conditions, maybe slightly deeper in exhumed slabs, and just dry peridotite with a little bit of serpentine in it, and didn't have evidence for any hydration. Maybe that's the solution. The other question is the crust involvement. Why does the crust only play a very minor role? And as we see in all these earthquakes in worm slabs. And we think the reason is is also because of metamorphism. As the slab goes down and various minerals, hydrous minerals break down, and the overall tendency is that the crustal rock will densify, will become denser rocks, and it will shrink volume, because the substratum, the mantle part doesn't shrink, or doesn't shrink as much, and the shallow part is shattered, and it fractures itself and shattered, and so it forms a poor condition, right, to have coherent rocks for a big rupture. And as a result, we expect this kind of distribution of the structural condition. And densification, shrink, and shatter of the shallow part, and deeper parts are more coherent For whatever reason, if you can make the slip seismic, and this slip the bigger slip tend to involve the mantle part or maybe the lower crust, and the upper crust plays a relatively minor role. So the conclusions are the thermal condition, the hypocenters for these earthquakes are around 600 degrees or less, and with some uncertainties. And the petrologic condition, there's a progressive crustal dehydration densification. Hydrous minerals in the slab mantle, and if present, and they're not actively dehydrating. And the structural condition is the upper crust is expected to be shattered. It's a more coherent mantle part, and the lower crust can host very large rupture. The remaining question is, if mantle hydrous minerals are not actively dehydrating, what facilitates seismic slip in the slab mantle in this depth range? Thank you.
So, we have some time for questions? Go ahead.
What's the role of pre-existing fracture?
Excellent question. Yeah, he just reminded me. I forgot to mention these fractures really expect to be pre-existing faults. Yeah. So yeah, that's excellent. Yeah, something I forgot to mention.
Mike?
I didn't quite follow why the slab would be getting colder with increasing depth as it's subducting, and that's sort of crossing an isotherm in the opposite direction. I didn't quite see why that would be happening in terms of the temperature of the slab.
Yeah, the slab is not getting colder, but it's not warming up fast enough. If you see the clip from a slope here, and the pressure increases a lot faster, but the temperature doesn't increase as fast. So you see, as a result, and it's actually moving away from the. So you have both pressure and temperature responsible for dehydration, right?
What is your uncertainty on the slope of that wide arrow?
Here, and that's from the thermal model, and the uncertainty should not be very large. There's uncertainties in the geometry of the slab. You can use a different geometry, but whatever geometry you have, you have the same issue. The temperature will not increase very much, and the pressure will increase a lot faster, right? So you can change it slightly depending on the slab geometry, but it's pretty robust.
The last question? Vala?
So why do you think these earthquakes in this lab are so large in Mexico and we don't really observe them?
Yeah, that's $1 million question. We are all surprised by the size of this earthquake. It's saddened. Yeah, well, yeah, and yeah, it's really if no special condition is required, we don't need the rupture to be confined in certain dehydration range. Maybe there's more freedom for the rupture to grow in the vertical dimension, and horizontally, if there's more a smoother structure to allow a pre-existing fault to allow that kind of rupture to happen. Yeah, so this is a good question. I don't really know the answer.
All right, well, I think we've had a great session. Thank you, everybody. Remember, we have the poster session. The posters are all the way in the back because it's the late breaking session, so it's way far away from everyone else. Thank you.